Welcome to Lecture 6 of Modeling and Simulation of Physical Systems, in which we shall discuss the modeling techniques for the mechanical systems containing both the translational motion elements as well as the rotational motion elements. Our lecture agenda mainly consists of two items, the first of them being the general modeling procedures. And this will be illustrated with the help of a trailing arm suspension system example. At the same time, we shall try to understand the limitations of the general modeling procedure, and as an alternative, we shall discuss an energy-based method known as famous Lagrange's method. This will be understood with the help of two examples. Both of them are the end chapter problems. The first one being the spring mass damper lever, and the second one, and perhaps the more complex one, being the rolling wheel and the pendulum disc problem, on which we are going to spend significant amount of time in this lecture. All right, let's get started then. The general modeling guidelines for the system of combined translational and rotational elements are already given in section 5 of the textbook. And we have already been practicing these guidelines as illustrated in our last two lectures. However, there are certain requirements which are specific to our new situation, which need explicit emphasis. The first of them being the identification of the degrees of freedom, and to be able to specify corresponding position or displacement variable. So in this case, we have to define, or first of all, we have to identify the number of degrees of freedom that can specify the configuration of the mechanical system. And for each degree of freedom, we need to specify the position or the displacement variable. For instance, we can use the linear displacement of any rotational motion element and specify a variable such as xi, or we can use theta to specify the rotational displacement of the rotational motion element. However, note that the description of these variables remain incomplete unless we establish a convenient axis system which provide a reference for these variables. So in that sense, perhaps I believe that the condition 2 is more important than condition 1, and perhaps it makes more sense to reorder these conditions. After the definition of the position or displacement variables and the establishment of the convenient axis, we proceed to the identifications of the nodes of the systems so that we can write down their corresponding equations of motion. In this case, a node can exhibit either a rotational motion or a translational motion, or both the rotational as well as translational motion. And this option C was particularly highlighted when we saw an example of a rolling wheel with a spring, where the rolling wheel node exhibited both the translational as well as the rotational motion, as we saw in our last lecture. Let us apply the general modeling principles to the trailing arm suspension system. It is a system which is commonly found in our automobiles such as cars. It is designed to minimize the impact of vertical displacement applied to the automobile tire so as to minimize its impact on the passenger sitting inside the car. However, the tire of the automobile needs to remain mechanically connected to some different parts of the automobile. One of them being the steering system that is responsible for orienting the tire. So here we say that the tire is connected to the steering system with the help of a torsion bar. The tire is not directly connected to the torsion bar. In fact, there is a rigid pivot arm modeled as a rigid link as shown here that is in turn connected to the torsion bar with the help of a bearing shown here. The bearing is here because this particular point on the rigid pivot arm is showing here as the pivot, so this is not going to move. However, this torsion bar that we shall later model after a torsion spring is going to rotate. Therefore, it is going to come in contact with this pivot which is stationary. Therefore, we need to add a bearing. The tire also needs to remain mechanically connected to the chassis of the car. However, at the same time, we need to minimize the impact of these vertical fluctuations. For that, we have a shock absorber that indirectly connects the tire to the chassis of the car. In fact, the shock absorber is connected to the rigid pivot arm that obviously is in turn connected to the tire, probably to the axle or the wheel hub assembly. So in order to model this system, we will actually refer to the simplified model. We first note that the rigid pivot arm is obviously modeled as a rigid link. The dimensions are shown here. The length of the link is R2, and this is the length taken from the pivot point to the end of the link. This rigid link is also connected to the chassis of the car with the help of a translational damper modeled with the help of a damping coefficient B. The distance between the pivot and the point where the translational damper is connected is R1, shown here. On the other axis, the pivot is connected to the torsion bar, modeled as a torsion spring with the spring constant Kt. The spring will in turn be connected to some other parts of the car, such as the steering system, but that is not included in the model as such. So we'll just say that the other terminal of this torsion spring is fixed or stationary. Likewise, the chassis is also assumed to be stationary. Therefore, there is no displacement on this end of the damper. But what about this tire model? The model of the tire also includes the wheel hub assembly. So in addition to the tire, we are also going to consider the wheel hub assembly in the model. In its simplified form, this model contains a mass spring system, as shown here. This mass accounts for the mass of the wheel hub assembly, and the spring, whose spring constant is K, represents the flexible part of the tire. Note that this system can be represented along three axes. The first of them being the x-axis, about which the torsion spring is going to rotate. So this theta rotation is taken along the x-axis. There is a y-axis, that is the axis along the length of the rigid pivot arm, and the z-axis, where we have the motion of the damper. as well as the motion of the mass spring system. How does this motion come about is an interesting question. So the way this system works is that the torsion spring is going to exert some torque, which is going to rotate this pivot arm about the x-axis. And there is going to be a rotation, corresponding rotation on the other end of the pivot arm. That is the end where the tire is attached, or the whole wheel assembly and the tire is attached. So there's going to be a rotational motion. Because the rigid pivot arm is a rigid link, so the rotation on both ends should be the same, that is theta. Note that the type of motion exhibited by the pivot arm is rotational by nature. So in summary, the torsion bar is modeled using a torsion spring. The shock absorber is modeled using translational damper, and the tire, and here I should really include the tire as well as the entire wheel assembly, is modeled as the mass spring system. The pivot arm is simply modeled as a rigid link described by the discrete inertia. The pivot arm and the tire mass, in fact the tire and the wheel assembly mass, rotate about the pivot, and this motion is a rotational motion, so we need to specify a rotational displacement variable such as theta. The axis of rotation is x-axis. An important assumption that we are going to take in this example is that theta is small. Hence, the small angle approximation can be established. The translational spring and the damper are going to be displaced along the z-axis. But we have to be a bit careful here because, like we said, as the pivot arm moves, it primarily exhibits a rotational motion, and the pivot arm is connected to both the translational spring and indirectly connected to the translational damper. They both exhibit the motion along z-axis, but this motion intrinsically is a rotational motion. But with the help of small angle approximation, we shall approximate this small rotational motion with the help of linear motion in writing the equations of motion for the translational spring and the translational damper. And obviously the torsion spring is displaced about x-axis. It actually represents the angular displacement. Another important assumption is that the tire and the wheel assembly does not rotate with respect to the pivot arm either in the clockwise direction or in the counterclockwise direction. Alright, so once the problem has been set up, it is useful to revisit the definition of the axis. So remember, x-axis about which the torsion spring is going to rotate. Then there's a y-axis along the length of the pivot arm, and the z-axis along which the translational damper is going to exhibit motion as well as the translational spring. Although the type of motion is not perfectly linear, but with the help of small angle approximation, that rotational motion, which is basically theta, is approximated as linear motion as described in the previous slide. Now we are ready to write down the equations of motion. And the first thing to note is that the pivot arm, assuming it will have a moment of inertia J0, is directly connected to the mass m of the tire as well as the wheel assembly. What we can do now is that we can lump the moment of inertia and the mass together into a single node and write down the equations of motion. What really facilitates this modeling technique is that the motion of the mass and the motion of the rigid pivot arm can both be specified by single displacement variable, that is theta. And that is because the pivot arm is rigidly connected to the part of the wheel assembly which has mass m. Alright, so with that in mind, let us proceed to write down the equations of motion. The intrinsic motion is rotational motion. So what kind of elements are connected to the pivot arm as well as the mass which is attached to the pivot arm? Well, so we start from the left hand side. We have a torsion spring. If we draw a free body diagram of the torsion spring, there is a counterclockwise rotation theta. So this is a side view of the rotational torsion spring, where the angular displacement used to describe the motion is in the counterclockwise direction. So in response, we can just say the spring is going to exert a clockwise torque, as shown here. In fact, the direction of the torque is incorrectly drawn. It should be in the opposite direction. So I apologize for this mistake. So this really should be in the clockwise direction. And we can write down the equation of the torque exerted by the spring, which is in the clockwise direction. Ts equals to kt times theta. Similarly, we can draw the free body diagram of the translational damper, whose damping coefficient is B. One end of the translational damper is fixed. There is no motion. The other end has some motion, which is basically a rotational motion, but with the help of small angular approximation, we can approximate it as linear motion. This is going to be R1 times theta dot. In fact, it will be helpful to understand where does this R1 theta comes from. So this R1 theta is, as shown here, is basically the length of an arc. When the rotation occurs about this pivot and the effective radius becomes R1, it is given in the problem, and the angular displacement is theta. So this is R1 theta. And if you take a time derivative, this becomes R1 theta dot. The damper torque has been assumed to be acting upward at the free terminal. Actually, this terminal is not free as such, but by that I really mean where the terminal of the damper where we have some motion. Fd, the damper force acting upward on that terminal, is minus B times R1 theta dot. So remember, R1 theta dot is a linear velocity on this terminal of the translational damper. Now comes the free body diagram of the spring. In this particular problem setup, we are assuming that one end of the spring is fixed, there is no displacement, and the other end, which is connected to the mass small m, exhibits some displacement. Again, this is primarily rotational displacement. However, we are interested in the linear displacement, the corresponding linear displacement applied to this terminal. So the arc length, as shown here in this diagram, is basically R2 times theta, because the distance from the pivot to this point, that is the point representing the terminal, the top terminal of the spring, is R2, and theta is the angular displacement. So this is R2 times theta, and the small angular approximation says that r2 theta can be taken as a linear displacement, and the force exerted by the spring on this terminal, that is over here at this point, is downward, and this is Fs equal to k times r2 times theta. Now that we have resolved the expressions of torques and forces applied by the rotational as well as translational motion elements, we are ready to write down the final equation of motion for the node that is made up of the discrete inertia of the pivot arm combined with the mass of the tire, J0 and M. But before we do that, we recognize that the combined discrete inertia and the mass primarily exhibits the rotational motion specified by the displacement, angular displacement variable theta. Although this node, that is the combined discrete inertia, rigid pivot arm, and the mass, experiences loading in the form of torques as well as in the form of forces applied by the rotational elements and the translational elements respectively. However, because the motion of this pivot arm and the tire is rotational by nature, so the Newton's second law of motion that leads us to write down the equation of motion should be balancing the torques rather than the forces. Therefore, we are going to convert these forces into the torques. So the other loading is already in the form of torques, that is the torque applied by the torsion spring, Ts. The expression was calculated in the previous slide, Ts equals to kt times theta. The direction of this torque is clockwise. The torque due to the damper will be the force multiplied by the moment arm. And in this case, the moment arm is the radius r1. And this damper force is responsible for exerting a counterclockwise torque, that is the force multiplied by the moment arm minus b r1 squared theta dot. And finally, the torque component due to the force exerted by the translational spring will be the spring force Fs times the moment arm, and in this case moment arm is the radius r2, that is the distance between the pivot and the terminal, the moving terminal of the spring where the mass m is attached. Fs times r2 equals kr squared theta, and this torque is applied in the counterclockwise clockwise direction as shown here, and that's because the force, the spring force, is acting downward and it is acting against the displacement variable theta. So now we have all the torques ready. We can just tack this onto the final expression, where the right hand side is the net moment of inertia of the pivot arm and the mass associated with the tire and the wheel assembly, simplified as mr square, where r is the radius of the tire. So J0 plus mr squared times theta double dot equals to minus Ts. That's because the torsion spring torque is opposite to theta, so minus Ts, minus Fs R2. That's because the translational spring force is applying torque that is opposite to theta, plus Fd times R1. This is because the damper force Fd is exerting torque which is in the direction of theta. Once again, it is important to emphasize the correct signs in the equations of motion. Substituting their values gives us the final equation of motion as J naught plus mr square whole multiplied by theta double dot plus b r1 square theta dot plus k r square theta plus kt theta equals to 0. Let us now consider a more realistic scenario in which the tire and the wheel assembly will experience a vertical displacement. It occurs when the automobile is driven on a bumpy road. In this case, the bottom terminal of the spring in the model of the trailing arm suspension system can no longer be assumed fixed. In fact, there is some motion specified by the displacement u of t. This is a vertical displacement and it is acting as the input to the system. In your homework exercise, you are going to relate the input displacement u of t with the angular displacement of the pivot arm. The differential equation of this relationship is essentially the same as before, with the exception that the right-hand side is no longer 0. In fact, it is now equal to the input displacement u of t. So what is the main takeaway of this example? The main lesson learned from this example is that because our model of mass or discrete inertia assert that these elements shall not exert forces. Therefore, in this case, when we saw that there was two rigid bodies, one of them being the rigid pivot arm, was directly connected to the tire and the wheel assembly, we came across a situation where there were two masses, or one of them being the mass, the other one taken as the discrete inertia, were connected. But how can we model the forces being applied to the moment of inertia of the pivot arm and the mass of the tire and the wheel assembly? So one of the problem was that because masses and the inertias are not modeled as the force or torque generating elements, should you need to write down the equation of motion for the two? If the two are mechanically connected, as in this case, then it makes more sense to lump them up into single mass or discrete inertia, provided that they both experience displacement, either linear or angular. In our case, it was the angular displacement theta that was specifying the displacement for the mass of the tire and the wheel assembly, as well as the displacement of the rigid pivot arm. Because both the tire and the wheel assembly and the rigid pivot arm displacement could be specified with the help of same displacement variable theta. In fact, it is exactly the same for both the mass and the pivot arm. Therefore, the lumping was really helpful. But note that there are scenarios where this type of lumping is no longer possible. And one of the main reasons is that the two mechanically connected bodies corresponding to the mass or the discrete inertia have different angular or linear displacements. They can no longer be described by a single displacement variable, as we shall see in the next example. Let us now consider another interesting example of a system containing both the translational as well as rotational elements. This is an example of a mass spring damper lever system, an end chapter problem. In this problem, we have a lever which is pivot over here, and it shall exhibit a rotational motion about this pivot. The lever is experiencing a force F of t on its bottom end over here. The other end of the lever is connected to a mass damper system. through a rigid link. Note that the lever itself will be modeled as a rigid link. Now in this case, because the rigid link of the lever are directly connected to the mass, we once again run into the problem where the mass and the rotational discrete inertia describing the motion of the lever, both the elements are directly coupled. However, note that the mass is expected to exhibit linear displacement as shown here. So if the force displaces the lever at its bottom end to the right hand side, then the lever will exhibit a rotational motion specified by the angle theta, and as a result, on its upper terminal, it is going to move left and pushes the mass leftward, and therefore the motion of the mass is a translational motion. So there are two problems in coupling the discrete inertia of the lever and the mass m here. One of them being that the mass has different amount of displacement compared to the displacement of the lever. And the other problem is that the mass is exhibiting linear displacement, whereas the lever will exhibit a rotational displacement. Now obviously, here again we can utilize a small angle approximation to somehow approximate the angular displacement of the lever by means of an approximate linear displacement. But how can we solve the problem of different amount of displacement experienced by the mass and the lever? So in this case, we are going to refer to a new technique known as the Lagrange's method. Lagrange is basically an energy-based method for writing the equations of motion. What this means is that we primarily deal with the energy of the system, which can be further decomposed into component energies such as kinetic energy, potential energy, and the dissipation energy. So we're all familiar with the kinetic and the potential energy. The kinetic energy is associated with the motion, and the potential energy is associated with the height of the system, or in case of spring, we have an expression for the potential energy stored in the spring, and it has analogies across various disciplines. Then we also have a dissipation energy, which is a bit of a new concept here. It is an energy dissipated by the system, such as we can model the energy dissipated in response to overcoming the frictional forces, or if there is a damping effect in the system, then there is going to be a dissipation energy. All right, then we need to define reference axes as before, and these reference axes then in turn define the displacement variables, Qi in this case. So there is an overlap in setting up the problem or the model, as was the case when we discussed the general guidelines for modeling system containing both the translational and rotational motion elements. So the reference axis is again emphasized. We need to define a reference axis based upon which we describe our displacement variables, Qi. Next, we need also to identify the loading. By that we mean the force or the torque represented by capital Q which is going to be a function of a corresponding displacement variable, small q of I. So this loading, a force or a torque, will act on a point where the displacement is q of I. And this is perhaps the most important point to understand. The loading in the Lagrange method are associated with some specific displacement variable. And we say that the loading is a function of displacement variable, and it should act on a point in the system where the displacement is q of I. Very often this loading function, capital Q of small q of I, constitutes the input to the system. Now let us try to understand how to apply Lagrange's method to construct the model of a mass spring damper lever system. Again, we are less interested in deriving the expression of the Lagrange equation or to explore how did this expression come from in the first place. Instead, we are more interested in applying it to our examples and in different scenarios. So in Lagrange method, the right hand side is the loading function, capital Q, bracket small qi, which is just saying that the loading function is a function of some displacement variable qi. Again, this loading function is either force or a torque. On the left hand side, the expression is rather involved. It involves some partial derivatives, as you see here, and some time derivatives. So the expression can be read as follows. Take a time derivative of the partial derivative of t, and t is the kinetic energy, remember. So partial derivative of kinetic energy with respect to the velocity qi dot minus partial derivative of kinetic energy with respect to qi. Now this is just qi as the displacement. It is different from qi dot where it was actually the velocity. So partial derivative of kinetic energy with respect to the velocity qi dot needs to be computed, as well as the partial derivative of kinetic energy with respect to the displacement variable qi. We also need to add the partial derivative of dissipation energy with respect to qi dot. So again, it is a partial derivative with respect to qi dot, that is the velocity. And the final term in the sum is the partial derivative of potential energy with respect to qi. Here, this is a displacement qi. One of the reasons that you may think or you may wonder, why do we need partial derivatives? That's because the energy functions describing kinetic, dissipation, and potential energy is in fact or it can be a function of multiple displacement or velocity variables. So therefore, we need to calculate the partial derivative. Now this is one Lagrange equation for qi, small qi. That is, we have written a Lagrange equation for one displacement variable qi. If you have multiple displacement variable, then there are going to be corresponding multiple Lagrange equations, and we shall see that with the help of examples as well. But note that the choice of qi, that is the displacement variable, is very, very, very important for the correct application of Lagrange method. And further emphasizing, in fact reiterating, the fact that Qi is taken as the displacement at a point where Q is applied. Additionally, Lagrange's method asserts mutual compatibility between the displacement variable and the corresponding loading function Qi. So this mutual compatibility requires following conditions. That is, if Qi represents linear displacement, then capital Qi should be the force. And if small qi represents the angular displacement, then the corresponding loading function capital Qi must be torque. If we apply Lagrange's method to the mass spring damper lever problem, we first need to calculate the kinetic potential and the dissipation energy. For that, let us first consider the displacements of different elements. The lever is pivot over here, and it is demonstrating a rotational motion specified by the angular displacement theta. However, the other elements are primarily the translational motion elements, such as the translational spring, mass, and the translational damper. So if we look at the translational spring, its right terminal has been displaced by angular displacement because its terminal is connected to the lever over here. So although the fundamental rotation of the right terminal of the spring is rotational, we somehow need to convert it back into the linear displacement. For that, we can once again fall back on the small angle approximation, and we say that the linear displacement of the right terminal of the spring is equal to x2, where x2 is the arc length over here, the arc length, this one. The radius is a, and the angular displacement is theta. This is basically theta. So the arc length is a times theta. This is equal to x2. Now, based upon small angular approximation, x2 can be considered as linear displacement. Hence, a theta can be considered as an approximation of linear displacement. Likewise, the displacement of the mass is again x2, based upon the argument that the arc length here is a times theta, same as that of the displacement on the right terminal of the spring. So the mass also, the right terminal of the mass over here, it also experiences the leftward displacement, x2 equals to a times theta. Then comes the force. The force is applied to the bottom end of the lever where the arc length is different. Now this is x1. This is equal to 2a times theta. So if we think about setting up our model, considering that there is a single displacement variable that describes the entire dynamics of the system, that can be taken as q, small q equals to x1. The other displacement variable that is appearing and seems to be associated with the spring and the mass m is x2, but that is just half of x1. So really, there is only one independent variable, either that can be taken as theta or x1 or x2. So in this case, we have selected q equals to x1. Then the corresponding loading function, capital Q, that is associated with the displacement x1, we need to identify the point where the force is applied. this point is here. Over here, we have a loading in the form of force. So by necessity, this capital Q must be set equal to the force F of t. This is the input force applied to the bottom end of the lever. So let us write down the kinetic energies of the system. We can either directly write down the kinetic energy functions in the form of x1, or in form of theta, or in form of x2. But for the sake of convenience, we first write down the kinetic energy of different elements in the form of x2, although you can directly write them down in the form of x1, but here I've written down in the form of x2. Later they'll be converted back to x1. So the kinetic energy of the mass is half times m times the velocity squared. So the velocity of the mass is x2 dot. This is x2 dot. Now note that we don't care about the direction of x2 as such, because it is going to get squared. So even if it is leftward or rightward displacement, because it is squared, so that doesn't matter in the energy function. The potential energy in the system is due to the translational spring. Spring constant is k. That is half times k times x2 square. Again, we don't have to worry about the direction of displacements as such. And the dissipation energy, this might be new to you, but that's basically half times the damping constant b times the velocity of the damper, which is basically the same as the velocity of the mass, because the other end of the damper is fixed. So there's the only motion on the damper is on its right terminal where the mass is connected, where the velocity is x2 dot. So that's half time b x2 dot square. All right, let us now calculate the partial derivative to set up the Lagrange model. So partial derivative of kinetic energy with respect to x1 will be split into, using chain rule, as partial derivative of kinetic energy with respect to x2 times partial derivative of x2 with respect to x1. And that's because our displacement variable associated with the loading is x1, not x2. So that's become half partial derivative of kinetic energy with respect to the partial derivative of x2. And x2, remember, is half of x1. Likewise, we can calculate the partial derivative of kinetic energy with respect to x1 dot. Now this is not displacement, it is the velocity. But if you think about it, x2 dot is still half of x1 dot. That's because if you take a derivative on both sides, like over here, and if you take a derivative over here, d over dt, you're going to get this expression, x2 dot equals half x1 dot. So again, splitting this expression using chain rule gives us the partial derivative of kinetic energy with respect to x2 dot times partial derivative of x2 dot with respect to x1 dot. And that is half times partial derivative of kinetic energy with respect to x2 dot. And finally, partial derivative of potential energy with respect to x1 is just half of partial derivative of potential energy with respect to x2, as well as partial derivative of xr with respect to, this really should have been x1 dot. I apologize for the typo. So that's half times partial derivative of r with respect to partial derivative of x1. Again, there is a typo here, so that's basically x2 dot. So I'll fix that in the revised version. Once the partial derivatives have been computed, we are now ready to write down the Lagrange equation. So we already know what is partial derivative of kinetic energy with respect to x1 dot, as well as partial derivative of dissipation energy with respect to x1 dot, and partial derivative of potential energy with respect to x1. And we also know what is partial derivative of kinetic energy with respect to just x1. So tag those expressions into the Lagrange's equation gives us following expression: half m times x1 dot, and then we need to apply also the time derivative. Remember, the first term of the Lagrange is a bit different. It involves two derivatives. The first one being the partial derivative with respect to the velocity variable, and after that it's a time derivative. So remember, two derivatives in the first term. The second term is 0. That means the kinetic energy with respect to x1 is 0. But kinetic energy partial derivative with respect to x1 dot, that is non-zero. In fact, that is half times x1 dot. As a homework problem, you are required to show that why is it that the partial derivative of kinetic energy with respect to x1 is 0, and that actually boils down to the problem of showing that the partial derivative of x1 dot with respect to x1, that is equal to 0. So if you can show this identity, then you can show that partial derivative of kinetic energy with respect to x1 is actually 0. Simplifying this expression gives us an expression, and obviously the right hand side of the Lagrange is equal to capital Q, which is just force. After simplification, we arrive at an expression that is relating Ft with respect to with x2 as mx2 double derivative plus b times x2 dot plus k times x2. And if our goal was to show a relationship between Ft and theta, so where theta is the angular displacement of the lever arm, then we can now relate theta with x2, which basically x2 is a times theta. So tag this value into this equation, recognizing that if x2 equals to a theta, then x2 dot equals to a times theta dot, which is fairly straightforward, knowing that the derivative on the left hand side will make x2 as x2 dot, and the derivative on the right hand side will make theta, will convert theta into theta dot. And likewise, the double derivative of x2 equals to the constant times double derivative of theta 2. That is by taking double derivative on both sides of the equation over here. So the final expression is 2 times f of t equals ma theta double dot plus ab times theta dot plus ak times theta. Now in this problem, we assume that the mass of the lever is 0. So the m is 0. Therefore, the moment of inertia for the lever was equal to 0. However, if we do include the mass of the lever, if that is taken as m, then as part of your homework, show that the expression obtained from the Lagrange's equation will be the same except for the first term that is going to get doubled. So that will be 2 times mass m times the parameter a, describing the length of the lever, and then theta double dot. So only the first term will be changed, right? Our last example, and perhaps the most complex of the 3 problems of this lecture, is about the model of a rolling wheel and the pendulum disc. it asks us to relate two angular displacement. One of them is phi, describing the angular displacement of the rolling wheel, and the rotational displacement of a pendulum which is hanging from the center of the rolling wheel. The pendulum is connected to a disc at its bottom. So two angular displacement phi and theta must be related, and for that we need to find out the equations of motion for this system. Again, we are going to rely upon the Lagrange's method, but first we have to list the modeling assumptions as before. The first thing is that the top wheel, this part, it's a wheel that is going to roll on the surface without slipping. So this is a case of a rolling wheel without slipping. There is no slipping and the wheel is going to roll, and this angular displacement shows that the wheel is probably going to roll in the leftward direction, although that is somewhat irrelevant in setting up our model. The other assumption is that the pendulum is hanging from the center of the wheel, essentially the center of gravity of the wheel, CG1, and there is no friction between the point of contact. So there's no friction between CG1 and the point where the pendulum is hanging from. The third assumption is that the bottom disc, this disc, is rigidly attached to the pendulum. That is, it is not going to rotate with respect to the pendulum. And a pendulum is a rigid link whose mass is negligible. So the only messy part are the top wheel and the bottom disc. The mass of the pendulum is negligible. However, in this case, unlike as we did in previous examples, perhaps in our last week lecture or before that, the weight of the bottom disc must be taken into consideration. In fact, this is an essential part of a pendulum problem. The weight of the pendulum is responsible for its oscillatory motion. In order to write down the Lagrange's equation of motion, we need to calculate the component energies of the system. First, recognize that the system indeed has some kinetic energy, T, and that is primarily attributed to the mass of the wheel and its inertia. So the mass of the top wheel is m1. It has radius r1, and also has the discrete inertia jc1, that is due to its motion about its cg1. So remember, the wheel, when it rolls without slipping, it has two types of motion. As the wheel rotates, let's say in this direction, then obviously the center of gravity of the wheel is shifted leftward. At the same time, the wheel also rotates about its center of gravity as it moves forward. So therefore, we need both the information of its mass as well as the discrete inertia parameters. The length of a pendulum hanging from CG1 is L. So this distance essentially is L. L is a distance, straight line distance between the center of gravity of the top wheel and the center of gravity of the bottom disc, which is connected to the bottom end of the pendulum lever, pendulum R. The disc connected to the pendulum, or the pendulum disc, or occasionally we are going to call it the bottom disc, has a mass m2 and it has discrete inertia jcg2. What do we mean by that? So the mass of this bottom disk is m2 and it has associated center of gravity cg2 where the whole mass appears to be concentrating, but it also has a discrete inertia cg2. By that we mean because this disk is going to exhibit a rotational motion in this direction as shown here. It is going to exhibit a rotational motion about the z-axis. Let's say if this defines the x-axis of the system, and if this defines the y-axis of the system, and if the z-axis is taken out of the plane such as this, then the rotation of the disk, so this is the z-axis, so the rotation of the disk is about the z-axis, and so therefore it is going to assert the discrete inertia equals to jcg2. Hence the kinetic energy of the system, the total kinetic energy of the system, has two components, one of them being the total rotational kinetic energy, whose expression will be written first, and that will be followed by the expression of total translational kinetic energy. And at this point I should emphasize that the bottom disk, like the top wheel, has both the linear as well as rotational motion. The rotational motion is the rotation about a z-axis, which is directed out of the plane, but it also has linear motion specified by the linear motion velocities. So that is because the bottom disk has a tangential velocity in this direction or in this direction, and this tangential velocity vector can be decomposed into the velocity vector along x-axis and the velocity vector along y-axis. And we shall further explore this decomposition in the next slide. So right now, should we want to write down the expression of rotational kinetic energy, then what are the components of rotational kinetic energy? Well, one component is the rotational kinetic energy of the top wheel. The top wheel is going to rotate about its center of gravity as it rolls along the x-axis. The rotational kinetic energy has expression half times the inertia times the angular velocity. So the inertia is jcg1 because we are talking about the discrete inertia of the top wheel times its angular velocity, that's phi dot square. Then comes the bottom disk, that is the pendulum disk. The pendulum disk is going to rotate about z-axis, and the center of gravity and then the inertia of this rotational motion is given in the problem, that is jcg2. But what about the angular velocity? Well, this is theta shown here. This is essentially theta. This is going to get cluttered cluttered by the red color here, but if you go back one slide, it is basically theta. So theta dot square. So rotation about z-axis. So this essentially is the rotation about z-axis, which is connected with x-axis and y-axis at cg1. So the total rotational kinetic energy is half times jcg1 times phi dot square plus half times the jcg2 times theta dot square. So in the nutshell, what we have just written is the expression of total rotational energy of the system, which is attributed to the rolling of the top wheel and the rotational motion of the pendulum disc. I would now like to turn your attention to the translational kinetic energy of the system. First of all, note that the top wheel has translational kinetic energy, which is attributed to its center of gravity CG1 motion along x-axis as it rolls along x-axis. The velocity, linear velocity at its center of gravity VCG1 equals to radius times the angular velocity phi dot. Hence, the translational kinetic energy of the top wheel is half times its mass m1 times velocity vcg1 dot square. But the situation is more interesting for the bottom disk. And actually before that, we should realize that the top wheel has no velocity in y-axis. Now comes the bottom disk. The disk has linear velocity, which can be decomposed into both the x and the y-axis. Why is that the case? Let's consider the situation here. The disk has velocity. You can say this is the tangential velocity of the pendulum and the disk system as it rotates about z-axis and makes an angle theta with y-axis. This tangential velocity can be decomposed into the x-axis and the y-axis as shown by the vector algebra here. So the tangential velocity vcg2 of the disk is a vector sum of the y component of the velocity and the x component of the velocity. So this shows the importance of defining appropriate axis system before setting up the Lagrange's equation. Without the axis, you couldn't have realized the fact that the disk has a linear velocity that needs to be decomposed into or decomposed along the axis systems, x-axis and y-axis. Therefore, the disk kinetic energy must be the sum of kinetic energy components in both the axes, that is, the kinetic energy along x-axis and the kinetic energy along y-axis. However, in order to write down the expressions of corresponding kinetic energies, we first need to describe the position variable to facilitate the velocity expression for the disk. So let us say that xcg2 describes the displacement of the disk along x-axis and ycg2 describes the displacement of the disk along y-axis. Then, using the geometry of the system, we can write down the expression of xcg2 and ycg2 as shown here. And that essentially is a problem of geometry and trigonometry. So if L is the length of the lever, that is the straight line distance between the center of gravity of the top wheel and the center of gravity of the bottom disk. And if this lever, if this pendulum L makes an angle theta with y-axis, then the distance between CG1 and this distance is very important because it says that it is defining the initial position of the top wheel center of gravity. So in this diagram, all we are saying is that as the wheel moves to the left, then the center of gravity also moves to the left. So this dot represents the initial position of the center of gravity of the top wheel, which has now been displaced to the left hand side by an amount r1 phi, and this is along x-axis. Then in this distance we need to add another distance component which connects the center of gravity new location x coordinate with the center of gravity of the bottom disk CG2, a straight line distance, this one, and that is nothing but L times sine theta. So essentially xCG2 is the sum of r1 phi plus L times sine theta. What about the y component of the center of gravity of the bottom disk, yCG2? That is easier to compute. Essentially this is yCG2 is L times this distance, so L times cosine theta. And for the sake of the correctness of the notation, it is reminded that theta and phi are time dependent variables, even though we don't mention them as an explicit function of time, but it should be kept in mind at all times that phi and theta, they are actually a function of time. They are time dependent variables. So these are actually theta of t and phi of t respectively. Now that we have described the position variable of CG2, our next step is to convert those position variables into velocity variables so that kinetic energy can be found easily. So if we take a time derivative of xCG2, that is basically r1. This is r subscript 1. 1 in the subscript may not be visible, but this is r1, the radius of the top wheel, times the time derivative of phi, which is essentially phi of t, as we emphasized before, plus L times the time derivative of sine theta, and theta is again function of time, as we just discussed. So this simplification for x dot CG of 2 requires the application of the chain rule, particularly to the second term, where we say that this theta, because it is a function of time, so we first take a derivative of sine theta. So we are essentially taking derivative of a function of theta. So that will be the derivative of the function. The sine theta becomes cosine theta times the derivative of the theta with respect to t. So this gives you x dot CG2 is r1 phi dot plus L cosine theta times theta dot. So this is the second term is actually product of L cosine theta and theta dot. And once again, the theta t is essentially theta. So sometimes we switch between this notation for greater clarity, but we should keep in mind that theta t and theta, they are the same. Then comes the time derivative of the y component of CG2, that is y dot CG2, equals L times the time derivative of cosine theta. This is going to give you L minus L times sine theta times theta dot, again with the help of the application of the chain rule. Then if we take a product, if we square the terms, x CG2 is square, so this really should have been square here, and this is y CG2 dot square. When you open the square, you get r1 square phi dot square plus L square cosine square theta, theta dot square, plus 2LR1 cosine theta, theta dot phi dot. Likewise, y dot cg2 square is simply L square sine square theta times theta dot square. And hence, the total kinetic energy of the system will be the kinetic energy of the bottom wheel as well as the kinetic energy of the top wheel. And remember that in case of the bottom disk, the pendulum disk, the kinetic energy is further split into the kinetic energy due to the motion along x-axis and the kinetic energy due to the motion along y-axis. Adding up these two energy components will give us the total kinetic energy of the bottom disk, the kinetic energy due to the linear motion of the bottom disk. See, that is specified by the motion, linear motion of CG2 along x-axis as y-axis. So adding the two previous expression will give us the expression for the linear motion kinetic energy of the disk. And here you notice that the cosine square and sine square terms, they are added up to give you L square phi dot square. And everything else is pretty much the same. And finally, we also need to think about the linear motion kinetic energy of the top wheel that is associated with the motion of its center of gravity, CG1. So how far to the left, or in other case, how far to the right this CG1 has been displaced? That displacement variable is xCG1. That is simply R1 times phi. So this the distance covered by the wheel is just R1 times phi. This is how far the center of gravity will be displaced. And then if you take a time derivative, because in kinetic energy expression we are interested in velocity rather than displacement, so xCg1 derivative will be R1 phi dot, and squaring that, R1 square phi dot square. The kinetic energy expression will then further multiply this with half times m1. And the rotational kinetic energy expression has already been derived. That is well known. Half times CG1 phi dot square plus half times JCG2 phi theta dot square. And finally, we can write down the expression of total kinetic energy of the system, which is expectedly complex and containing as many as 1, 2, 3, 4, 5, and 6 terms. So we combine all of these terms, we add them together, and we arrive at the expression of the total kinetic energy of the system. And as a side note, remember that the center of gravity of the pendulum and the disk is at CG2. So this is where the entire mass of the pendulum and the disk appears to act. Just remember that. Once the expression of total kinetic energy of the system has been written out, our next task is to find the partial derivative of the kinetic energy with respect to the displacement variable. Now, what are the displacement variables chosen in this case? Assuming that there is some torque which is applied to the bottom disk, and there is some torque which is applied to the top wheel, and hence both of them are exhibiting motion. But in the problem setup, no such torque has been given. So we can just simply assume that the loading over here, so Q of theta is actually equals to 0 because no loading has been given. So Q, let's say just Q1 of theta is equal to 0. And here again, in the problem, there is no loading that is explicitly given. So we can just say Q2, which is now a function of this angular displacement phi. That is not given, so that is just equals to 0. So our displacement variables, as we shall see in about 2 slides, that those displacement variables to be used in the Lagrange equation are phi and theta. Could have been different, but in that case the problem setup would have been changed dramatically. And also from the fact that in the final expression we need to relate theta with phi. So considering that our displacement variables are going to be phi and theta, although the corresponding loading are 0, so we are going to calculate the partial derivative of kinetic energy with respect to phi dot first and get this expression. The rest is just algebraic manipulation, but it's important to systematically compute these derivatives so that we can correctly write down the Lagrange equations of motion. Then the time derivative of the partial derivative of kinetic energy with respect to phi dot, this expression. The partial derivative of kinetic energy with respect to theta dot. The time derivative of the partial derivative of kinetic energy with respect to theta dot. And partial derivative of kinetic energy with respect to theta. And partial derivative of kinetic energy with respect to phi will be 0. And then it will be helpful to write down part of the Lagrange equation already, although we haven't yet computed the other energy components such as the potential and the dissipation energy. So the first two terms of the Lagrange equation, the first Lagrange equation will be the partial derivative of kinetic energy with respect to phi dot followed by its time derivative minus partial derivative of t kinetic energy with respect to phi. And there will be a second Lagrange equation in which we are going to take partial derivative with respect to theta dot and theta. Will give us this expression. So we have pre-computed these expressions so that by the time we have computed the other partial derivative of the Lagrange equation, which involves potential energy and dissipation energies functions, we are ready to simply write down the final equations of motion. All right then, what about the potential energy of the system? Notice that there is no spring in the system. However, in the pendulum problem, in the classical pendulum problem, we know that there is a potential energy by virtue of the height of the pendulum. So we're going to use the potential energy function described in the form of the height. So the height of the system is essentially the height of the pendulum. Basically, that means the height of the center of gravity of the bottom disk. So the potential energy of the system can only be attributed to the height of the center of gravity of the disk as the disk rotates about z-axis. Let h represents the height of CG2 above its lowest point. So what is the lowest point of CG2? That is when the yCG2, the y component of its displacement, equals to L. yCG2 equals to L. And the height is going to be L minus the current y position of CG2. So essentially we are saying that if this is the current position of CG2, then its y coordinate subtracted from L gives us the height of the pendulum disk. That is same as L minus L cosine theta when we take the value of yCG2. And this is going to give us potential energy as mgl, where g is the acceleration due to gravity, times the length of the pendulum minus times 1 minus cosine theta. Once we have calculated the potential energy, then we can also compute the terms of derivative involving potential energy in the Lagrange equation. Those terms, there is actually just one term in each Lagrange equation that involves potential energy. That is, when we take the partial derivative of potential energy with respect to the displacement variable, one of them being phi. So because potential energy does not depend upon phi, that is just equal to 0. So remember that the only potential energy attributed to the system is due to the height of the bottom disk. There is no potential energy associated with the top wheel because its height never changes. It only exhibits motion along x-axis, and hence only contains kinetic energy. Then, what about the partial derivative of potential energy with respect to the other displacement variable, that is theta? That is going to be m2gl sine theta. Finally, what about the dissipation energy? Apparently, there is no friction that needs to be modeled in this problem, or the frictional effect has already been taken into account. So the dissipation energy is set equals to 0. No explicit dissipation energy formulation is required, so that is just 0. And hence any partial derivative of r with respect to any displacement variable will also be equal to 0. Now we have all the terms required to set up the Lagrange equation. The final thing to note is that there is no loading explicitly given in the problem. In fact, the problem statement says it doesn't say anything about the loadings, that is the force, external force, or the input force, or the input or external torque. So for each displacement variable, we can just set the corresponding loadings to be equal to 0. Hence, if we want to write down the Lagrange equation for Q1 and capital Q1, so then Q1 is taken as phi and capital Q1 will be 0. This is the equation. The left hand side involves derivative with respect to phi and phi dot. And by plugging the expression of each one of those terms, we finally arrive at the first equation of motion obtained from the Lagrange method. So which says that theta double dot plus m1 r1 square plus m2 r1 square plus jcg1 divided by lr1 cosine theta minus tan theta times theta dot square equals to 0. Similarly, we can write down another Lagrange equation for the other displacement variable, that is small q2 set equals to theta, and the corresponding loading is 0. In this case, the left hand side contains partial derivative with respect to theta and or theta dot. The right hand side is 0. Plugging in the expression for each term, we arrived at the second equation of motion, which says that theta double dot plus m2 lr1 cosine theta divided by m2l square plus jcg2 plus m2gl sine theta divided by m2l square plus jcg2 equals to 0. And these two equations completely describe the equations of motion as required. So with that, I would now like to formally conclude a long lecture. I hope you enjoyed listening to this lecture, and you may have a lot of questions, and for that we are going to hold our regular Q&A session on Thursday starting at 2 p.m. Till then, Stay safe and have a nice day. Bye bye.